I will present in this talk, I will present recurrent and predictive neural network and its application, I may say, on the fire detection use case. On this work, actually, we were collaborating and we are still collaborating with Prof. Cüneyt Güzeliş from Yaşar University, and we are also in the industrial part of the project, or let's say the work. We are collaborating with Osman Yıldız from EDS Electronic. And let me introduce myself shortly. I will not go into detail, but I would like to try to highlight my background on this area, on this topic. So I am currently pursuing my PhD in the Institute of Theoretical and Applied Informatics, Polish Academy of Science. My research area is mainly focused on the quality of service and security issues on IoT, the massive IoT, I may say, and my advisor is Professor Gelenberg. Besides that, in my master thesis, I also work on IoT, but in my bachelor science graduation project, I have focused on fire detection by using metal oxide gas sensors, which is the basis, which creates the basis of this work, today's presentation. After that, I have participated in several projects, but one of them was on my graduation project in undergraduate degree, and which is also on the fire detection, supported by TÜBİTAK. For that project, I have won the rank 1 in the Turkish competition by TÜBİTAK 2241, which is the industry-focused undergraduate graduation project competition. I won the first rank in all Turkey, and after that, my master thesis supported by TÜBİTAK as well, which is can be called as a distinction. And also, I won a small award recently by MDP. Over the years, I have some publications in the last couple of years, 2 or 3 years. I may say that I have, to summarize, I have 5 SAJ expanded, 1 Scopus, and 16 conference papers. And in all of these publications, 1 journal in high rank IEEE access, and 2 conference papers, and also a patent application is submitted, but other 3 publications are published, are focusing on fire detection. And in IEEE access, we have published 4 RTPN, recurrent and predictive neural network, which is the main focus of today's talk, actually. By the way, if you have any question, please ask me. Meanwhile, in the Q&A session, and I will read them. Maybe I can mention them while I am presenting, or I can answer directly at the end. Okay, let's start with my talk, which is on the recurrent and predictive neural network. First, I will try to explain the intuition, the methodology first, then I will focus on the application of it on the fire detection with the methodological experimental results. So to begin with, the motivation to design such neural network architecture, which is RTPNN, is to increase the forecasting performance in multivariate time series data. In this case, which is the fire data, which can be binary, considered as a binary, or which can be considered as a regression problem, but the input is multivariate because we have too many sensors in the environment to observe. So to this end, we design an architecture that automatically learn and predicts important trend of each time series feature in end-to-end neural network architecture. In this way, this learning and prediction structure enables to capture increasing or decreasing movement of the feature over time, because it enables to capture each trend, but it learns it. And meanwhile, it predicts also the level, not only the feature, not only the trend, but also the level, which is the smoothed version of the actual value of each time series feature in end-to-end neural network architecture. In this way, it is able to decrease the effects of outliers in the data set, because when you smooth out the values, considering the trend and other parameters, you are able to eliminate outliers. You are not affected anymore by the outliers, which means that this architecture also has ability to become more robust against outliers or abnormal effects in the time series data. And in the end, it fuses trend, level, and also the actual values of the features to generate a prediction result. To understand the intuition behind, I will make a simple example of time series with outlier. So we will see the effects. Let's assume we have such a time series with 6 elements, which is mostly linear, but at the 4th element we have an outlier. So to capture the trend, we see that there is an actual trend in this way, and considering this trend and considering this time series, we may know that this value, this point is the expected value, expected level of this outlier sample. So we may easily say that if we have the advanced knowledge on all time series, we may easily say that this sample is an outlier. But in real time, we don't have such an option because we have a current time which creates an information, which creates a time axis into past and future. And in the future data, we don't have any information which is not available yet. So you may not know if this sample is outlier or not. In this way, we can only know the trend and we can calculate the expected trend for the future samples. In this way, we may only know the actual level of this, but not that one until it occurs, which means that time passes and this feature becomes available. When it becomes available, we already knew that the trend will go like this because we predicted in that way. So we would now say that this is the smoothed level, this is the expected level of the outlier of this sample, so we can smooth it out. So we can observe the real effect of that value on the prediction results. So this idea is already presented since 1940s, and which is the idea of calculating trend and smoothed data based on exponential weighted moving average. It is also called double exponential smoothing, or single exponential smoothing also covers a part of it. And also these are based on the Taylor series expansions, but the difference between them is another problem to design a RTPN, and differently from those ideas, the basic ideas, is to solve a different problem, which is when we have a multiple time series input and one predicted output, we have different structure of problem, which is the first, the calculation of trend and level in the standard literature does not consider the relationship between inputs and the output. So it means that you may calculate for each time series data, you may calculate the trend or expected level or smoothed value, but you will not know, or you will not consider any relationship between inputs and the output of the data. And another thing is that in this trend and level calculations, both of them depends highly on the selection of the parameters. In machine literature, we may call them hyperparameters. But there, since these are the only mathematical calculations, these are the parameters. So to solve both of them, we propose the recurrent trend predictive neural network architecture, which internally calculates the trend and the level. In this architecture, you may see that we have data processing units, which are original in this architecture, and we have also fully connected layers, which are very common in all deep learning models, almost all deep learning models actually. And to this end, for each of the trend predictor and level predictor, we have a recurrent neuron. In this recurrent neuron, in the first of them, in the top one, we feed the actual value, current value of the feature and the past value of the feature, as well as we feed back the calculated trend, the predicted actually trend value into the back of this neuron, since it is recurrent neuron. So based on these three values, at each step, it predicts the trend value of the trend. So in this way, it calculates the trend in the first layer. And by using the second recurrent neuron, which is the level predictor, we have an input, we feed the feature value, and also we feed back to the level value. So based on this, it also computes to level. But of course, this is in the feed-forward structure, when we are going feed-forward structure. When we are training, as you can see, there are alpha I1, alpha I2, and beta I2, beta I1. These are the parameters, which are also considered as the connection weights of recurrent and predictive neural network of this architecture. So these are not different than the connection weights of the fully connected layers. In this way, when we are training our architecture, either in a supervised or unsupervised way, it doesn't matter. But let's consider supervised way. When we are doing backpropagation, so we are also minimizing outputs, considering these connection weights as well, these parameters as well. In this way, these are adaptive to the resulting output. So, and again, as I mentioned, these are exactly operating as defined in the trend prediction or level prediction in the double exponential smoothing or single exponential smoothing, but the difference is now these parameters are learnable parameters in the architecture, and these are defined, these are modeled as recurrent networks, recurrent neurons actually. Now, we have a general concept and we have a general idea how the recurrent trend predictive neural network works. Now, I would like to mention some for the fire detection case. In the fire detection, the current fire detectors based on considers either smoke or the heat. So there are two main types of fire detections currently used in industrial operations. In the first one, the smoke detectors only try to detect the smoke by using infrared LEDs, transmitter and receiver pairs, or just one pair, sense and receive data. Anyway, but in such cases, when you have a dust or any other particles, very small particles, you have a reflection on that, so it may cause false positive alarms. And since these false positive alarms are very irritating, these smoke detectors create very big problems in such cases. For example, if you are smoking at a public space or at a home, anywhere it is, if you have some fire detector, it will give fire alarm if it is a smoke detector. Or if you are cooking, it will again alarm the rings, alarm the bells, so it will say that it is a fire. It is very irritating and not useful at all. In most of the cases, people just shut them down, so they will not be irritated by false alarms. But shutting a fire detector down is more dangerous because in real fire cases, you may not know if there's a fire or not. And the other type is the heat detectors. Generally, in the heat detectors, there should be some level of heat, and if the temperature of the room achieves that threshold, then it gives some alarm. But to achieve that threshold, of course, some materials, some products, or your household appliances will burn down or will be damaged. Also, some persons, the health issues may occur in this period. So in here, there is not a false positive maybe much at all, but there are false negative alarms, which is more dangerous, but less disturbing. So both of them has positive or negative phases, but what we propose is that using multiple inputs, which are the multi-sensor fire detector, we may call multiple inputs to measure smoke, flame, temperature, humidity, and various dangerous gases which occur during the chemical process of the fire, such as carbon monoxide or carbon dioxide or oxygen. In both or in all of them, we may observe some changes during the fire situation. And when we feed them, you may see that there is a sensor data processing unit. In the first layer, we process each sensor data by individual sensor data processing units of RTPNN. Then we feed them to the fusion part, which is the fully connected part of RTPNN. We fuse the data. When we fuse them, we have an output of fire probability, on which you can apply threshold or not, just consider as it is as a probability of fire. So to just recap, we have this structure and we have, of course, equations for them to calculate forward pass. You can very easy to calculate for sensor processing unit with two equations, each of them by two equations. And the fusion part is the standard MLP or fully connected layer with matrix multiplication and nonlinear activation functions such as tangent, hyperbolic, or sigmoid. Okay. In our experimental work, we are using a publicly available dataset, which is a detailed and good dataset actually, with many different experiments. And in this dataset, we consider the subset of this dataset because some parts are inapplicable or cannot be used properly due to some failures in experiments. But the usable part contains more than 25,000 samples, and we have two inputs because of the current value and the past value. And we have 5 different features, which means that 5 different sensors we are considering for our application. And in our parameter settings, we didn't make any hyperparameter search or anything. We just set it up intuitively, which also gives some robust results because the results does not depend on any detailed search or time-consuming algorithms. Anyway, we set the number of hidden layers in the fire predictive part, fully connected parts, to the number of sensors, which is 5 in here, 5 times 3 minus h for each hidden layer, 1 to 3. So that's why we use 3 hidden layers, because it is universal approximator, so there is no need to use 4 or 5 hidden layers, or it is not logical to use less than 3 hidden layers to approximate such a complex function. Then, in our first result, maybe it is one of the most important, especially for the end product, is time to alarm. In time to alarm, we measure the average duration between the occurrence of a fire, which is labeled in the dataset, and the first true positive detection. And so when we measure that, we see that RTPNN achieves 11 seconds. RTPNN gives alarm in 11 seconds after the fire occurrence, while the most competitive models with RTPNN, such as Candle MLP, MLP, or linear regression, can detect fire in 22 seconds, which is highly outstanding performance by RTPNN. And of course, we have some other metrics which are very common especially in classification problems, such as area under rock curve, which is 0.99 achieved by RTPNN, while the LSTM can achieve 0.96. And when we look at the F1 score, which is the harmony, mean of precision and recall, which is most commonly used metric, we also see such difference between RTPNN and the closest performance by LSTM. And Also, I would like to show you the Matthews correlation coefficient because F1 score itself not very sufficient for the imbalanced data set, but Matthews correlation coefficient is more applicable for the imbalanced data set since it provides a balance measure for such data sets. And in here we see 8% difference between RTPN and LSTM, and it achieves 90% accuracy or 0.9 Matthews correlation coefficient score. Lastly, it is not maybe much important as the performance scores, but it can be considered as important for such industrial production or final products. The training time of our TPNN increases linearly with the number of sensors in our product, which is very good result because linear increase is not a problem at all. But also in any practical application of fire detector, due to the hardware cost, it is not very applicable to consider more than 5 sensors. So for the 5 sensor cases, it is 0.05 seconds per epoch. And in our experiments, we generally train our TPNN for 500 epoch or between 500 and 1000 epochs. So it is not a big problem to train it for 50 seconds. And lastly, for the execution time, we may see that it also sublinear, or we may say it is kind of linear with the number of sensors. And it is very acceptable since even for 20 sensors, which is not practical even, it is under 0.6 seconds. But for the practical case, for 5 sensor case, it is under 0.3 seconds. So these are all my presentation. This concludes my presentation. Any questions?
Thank you, Mert.
Thank you
for this nice presentation. I have a question.
Sure.
Let me start. Now, in this architecture, neural network architecture, in the first stage, in the first layers, a kind of feature extraction is implemented. Trend and level are the features. And this architecture is appropriate for processing time series.
Yes.
So the trend and level are associated to time waveform of the signal, which is a time function. Now, my question is related to the extension of these architectures for space-time functions. For instance, you may have an electromagnetic wave which propagates over the space, and it is not a function, only a function of the time. It is also a function of space coordinates. Now, what do you think about the extension of this architecture to process time-space signals? Electroencephalogram, for instance, we process EEG signal is an electromagnetic wave signal. We process it by some models which considers actually EEG signals which are recorded by a set of probes.
Yes.
And we consider them multi-channel time series.
Yes, of course.
But actually the probes are placed in different positions. So it is actually a time-space function signal it is. So what do you think about the extension of this architecture to capture trends in the space also?
Yes. Yes.
In addition to the trends in time.
Okay, let me
Okay.
let me tell my idea, my opinion. Actually, I would like to mention that as well. While I was presenting, I didn't disturb the logical presentation, but this structure itself also can be used the space, human, or between different features. Actually, today I wrote on some ideas. Maybe is also in the listener list here. Anyway, this can be also used to measure the trend in the space itself as well, but not both as it is, either one or other. But to measure the both of them, I think it can be considered as, I don't know how to implement it or how to provide it mathematically now, but maybe it can be considered to measure the Euclidean distance in here instead of a difference, time difference. It can be considered as a Euclidean distance of a vector, which provides both time and space positions. It can be possible, in my opinion.
Am I contribute something?
Sure, thank you.
Okay, thank you. It actually makes sense to make this kind of calculation in time, space, or only space functions. In the example Cüneyt Hoca talks about, there are also both time series and also captured from different locations. So maybe each sensor can be thought as one probe put on a human scalp, and there will be some time series like x1k, x1k minus 1. But I'm curious about something. In the EEG case, if probes are besides each other, if they are located near to each other, in this case, there should be some connection between them. Maybe there might be some extra weights which connects them. I'm just only brainstorming. Yeah. I'm not sure about it, but it's
also possible.
A very good study about it.
Yeah, or just taking your idea and further improving it. There can be another layer here, which is not fully connected, but partially connected between some of the data processors, which again feeds data from the maybe same location or related ones, then forwards it to the next layers.
In the EEG processing, they usually use independent component analysis or principal component analysis, especially independent component analysis. Maybe the next layer might be some processing unit which makes this kind of independent component analysis to extract the independent components, because there are several sensors, and these sensors are getting information related with each brain locations, and they are combined in some sensor. So maybe extraction inside this kind of architecture might be very useful for them.
Yes, for sure.
Mm-hmm. It's a very good presentation also. Thank you.
Thank you. Any other questions?
Actually, I have one more question about this architecture also. Here in the both trend predictor and in the level predictor, we have only one summation unit. And Cüneyt Hoca said that these are actually feature extractors. Are we put some functions inside these parts? I mean, like the full connected layer, instead of only summation. Is there? Is this will contribute to feature extraction? What do you think?
Actually, since we consider it as a direct representation of the trend prediction or level prediction, that's why we don't use any activation function, such nonlinear function in here. Of course, in real other applications, I mean, it can be useful, but it will be more complicated, and I don't think it will contribute much. But except such cases, for example, in image processing, if you are applying this architecture in image processing or similar to that, if you know that in any layer there shouldn't be any negative value, then there can be some activation function to prevent it, such as ReLU. But another, beside ReLU or such specific applications, I don't think it will contribute much. The nonlinear function will not contribute too much, I think.
Okay, thank you.
But it can contribute in this way. If you do not want to use 3 hidden layers in the fully connected layer, you can use non-linear activation function in the first layer, so which will create more deep nonlinearity. So you may remove one nonlinear function, one nonlinear layer here from the fully connected layers to decrease the complexity.
I see. Thank you.
Thank you. Questions? You may, if you don't have a microphone, you may also write in Q&A session, Q&A part of the chat. Do you have any questions? I think there is no more official questions. Maybe we can stop recording.
I have a question.
Okay.
It's a rather non-technical question, more like a kind of personal question, let's say. First of all, thank you very much for presentation and the well presentation of this wonderful idea. I just wondered, what fired you to, let's say, think about this topic and literally build a new algorithm, which is a neural network applied for fire detection systems. What was the first step?
The first step was actually, let me go back. Actually, it was what I explained in this simple example. It was come from single and double exponential smoothings with our discussions in 2018, I think, or at the end of 17, with Prof. Cüneyt Güzeliş. We were discussing consider the trend of the inputs to detect the fire. Then also we published a conference paper on that, which is called Trend Predictive Neural Network directly. But then we have expanded that idea to make it more robust and make it provided as a, or just propose it, let's say, as a full trainable and functional neural network model. It was the starting point of the idea.
Thank you very much. Now it makes sense.
Okay. I think there is no more official questions. If I can just stop the recording.
Okay, Mert, thank you very much for this nice presentation. Again, I think we hope in the future you will present with another topic or extension of this model and its applications. Thank you again. Thanks also for the participants.
Thank you for inviting. Thank you everyone for
Thank you.
listening as well.
Thank you. Thank you, Mert. Thank you very much.
Have a nice day. Bye-bye.
See you later. See you.